Now let's buckle in and do an example in 3D. Let's find the maximum or minimum of this function f of x, y, z is x minus y plus z over this solid region. X squared plus y squared is less than or equal to z is less than or equal to 4. So if we draw that over here, we have a bottom part where z is equal to x squared plus y squared. That's the bottom boundary of our region. It makes this kind of paraboloid shape. And our top is this flat surface where z is equal to 4. And so in this part, our boundary comes in two pieces. And just like when we were doing integrals, we're going to have to deal with those pieces separately when we solve this maximum or minimization problem. So let's figure out what the biggest and smallest this function can possibly get is on this three-dimensional region. The first thing we should do is we should take our function and we should find the critical points. The critical points are when the gradient is equal to 0, but the gradient of this function is 1 comma minus 1 comma 1. There's no way that that's ever 0. We can't have, in order to have a critical point, we would have to have our first component equal to 0, and our second component equal to 0, and our third component equal to 0, and that never happens. So there are no critical points. And that means that the maximum or minimum of this function is not on the inside. The max or min definitely has to be on the outside boundary somewhere. But the boundary comes in two pieces. There's a top piece when z equals 4, that's this flat surface on top. There's a bottom piece where z equals x squared plus y squared, that's the paraboloid on the bottom. And those meet at a common intersection, this one-dimensional region where both of those equations are true. Z equals 4 and z equals x squared plus y squared. So in particular, since those two things are equal, x squared plus y squared is equal to 4. So this is a circle of radius 2. In the plane, z equals 4. And now, to find the global maximum and minimum, we have to check the boundary. We have to check the top boundary for critical points. We have to check the bottom boundary for critical points. And we're also going to have to check the boundary of the boundary for critical points and figure out all those maximization and minimization problems separately. So let's do that. The top part was z equals 4. So to parameterize that, here's a parameterization. Phi of uv is u comma v comma 4. And we were inside the circle of radius 2. So we've got u squared plus v squared is less than or equal to 4. We substitute in our function f of x, y, z was x minus y plus z. So if I plug in u comma v comma 4 into that function, I get u minus v plus 4. That's our new function. Here's its gradient, negative 1 comma 1. So there's no critical points in the top. And so the maximum or minimum must be on the boundary of the boundary for the top region. Now we do the same thing for the bottom region. Our bottom part was when z was equal to x squared plus y squared. So we parameterize it. Phi of uv is u comma v comma u squared plus v squared over this same region. U squared plus v squared is less than or equal to 4. And we substitute in. Now when we substitute in u comma v comma u squared plus v squared into our function, we get u comma v u minus v plus u squared plus v squared. And the gradient of that is now 1 plus 2u comma negative 1 plus 2v. So for there to be a critical point, we have to have 1 plus 2u is equal to 0 and negative 1 plus 2v is equal to 0. That happened, the first one happens when u equals minus 1/2. And the second one happens when v is equal to 1/2. So there's only one critical point. It's at negative 1/2 comma 1/2. And we can plug that into our function. The value of this function when u is negative 1/2 and v is positive 1/2 is negative 1/2 minus 1/2 plus 1/4 plus 1/4. And so that's negative 1/2. But then we have to check the boundary of the boundary. So we had this top region and we checked for critical points on the interior of the top region, and we checked the bottom region, we checked for critical points on the inside of the bottom region, but we haven't dealt with their common intersection, the boundary of the boundary, this circle of radius 2 inside the plane z equals 4. We have to check for maxima and minima there as well. And this makes these kinds of three-dimensional problems a lot trickier. So when x squared plus y squared and z are both equal to 4, we can parameterize that. Like I said, it's a circle of radius 2 inside the plane z equals 4. So here's a parameterization. C of t is 2 cos t, 2 sine t, comma 4. And we can plug that into our function. We get 2 cos t minus 2 sine t plus 4. And we find the maximum and minimum of that. Here's its derivative, minus 2 sine of t minus 2 cos of t. And that becomes 0 when sine of t is equal to minus cos of t, or equivalently, the tangent is equal to minus 1. Tangent being equal to minus 1 means that it's a minus 45-degree angle, and so that happens when we're at 3 pi over 4 or 7 pi over 4, because those correspond to 3 pi over 4 is up this way, and 7 pi over 4 is down there. Like so. And so then we can plug in our values at these 2 points. If we plug in t is equal to 3 pi over 4, cos is root 2 over 2, and sine is minus root 2 over 2. So our value at the first one is 4 plus 2 root 2, and our value at the second one is going to be 4 minus 2 root 2. And so then technically speaking, we have to check the boundary of this parameterization, which is when t is 0 and t is 2 pi. And these points, the function takes the value 6, like so. And so our potential global maximum and minimum are negative 1/2, which is what we found on the bottom, 4 plus 2 root 2, and 4 minus 2 root 2, which is what we found on the edge, and 6, which was kind of the edge of the edge. The smallest of these is the only negative number on the list, negative 1/2, because 2 root 2 is slightly smaller than 4. And the biggest of these is 4 plus 2 root 2, because 2 root 2 is a little bit bigger than 2, and so this is bigger than 6. So that's the global maximum and global minimum. You can see that this is definitely a more involved process than it was in the one-dimensional case. But the step-by-step procedure is not super bad, and it's just checking for critical points repeatedly.